Okay guys, this is the last section in chapter 7 that we're going to be talking about. It's a really neat section of chapter 7. It deals with real life examples of exponential growth and exponential decay. I want to take a minute and tell you a little bit about exponential decay and tell you kind of oddly why exponential decay means a lot to me. Okay, it's going to sound kind of weird and you're just going to have to be patient and listen to the video and listen to my voice for a little bit, okay? A couple of years ago, or a few years ago, my dad had thyroid cancer, and he had to take this iodine pill. Now, it sounds kind of weird, but this iodine pill literally made like the cancer cells on his thyroid, it kind of made them like glow on a scan. Now, what was kind of cool was my dad had to take this pill, so my dad was actually like a little bit radioactive, and every day after he took this pill, his amount of radioactivity shrunk. So for a while there, I wasn't even allowed to be by my dad because they said, the doctors told him, they said, since you're actually technically radioactive, you need to stay away from your wife. You need to stay away from any woman who might have a baby in the future, anytime, because he was radioactive. Now, my dad's not really radioactive necessarily right now, but what happened is, this is going to look weird, but let's say my dad was this much radioactive. Okay, after a certain amount of time, like a week or something like that, it shrunk, and that's called the half-life of something. Everything that decays has a half-life, and so my dad's radioactivity, actually, if this was how much he had, it got cut in half in, like, let's say a week, and then if this is how much he had, it got cut in half in like another week. That's called exponential decay. So what happens is, with exponential decay, things tend to shrink really big, and then they shrink a little more, then they shrink a little more, then they shrink a little more. Now, technically, yeah, my dad will always have a little bit of radioactivity inside of him, but it's just kind of a neat story. That's exponential decay, where you start with a lot, you cut it off, and then you cut it off, and then and based on whatever that is, doctors are pretty smart people. They're going to have that formula. And so anyway, that's how exponential decay grows. How does exponential growth happen? Exponential growth, the best example I can give you, and I would be writing these down, exponential growth would be like, it sounds kind of wrong, but you leave two little bunnies in a row, you leave a boy and a girl bunny in a room, you know, you come back 4 months later, provided they had enough food, or how many ever months later, a couple of years later, whatever, you're going to have a lot of bunnies, right? That's the best example I can give you of exponential growth. But exponential decay, like I said, is kind of cool, because I know my dad's doctors actually had to figure out when my dad could safely be around me and my mom and other people. So anyway, let's go ahead and get started first with exponential growth. Now, my husband, this is the last video I'm making because all the other videos after this I actually made last year. So I told my husband, I'm like, you should guest appear in my last video. So say hi.
Hi, children.
So he's going to help me. He's going to show you how easy this stuff is, because when was the last time you were in Algebra 2?
I don't know.
12 years ago.
12 years ago.
12 years ago he was in Algebra 2. So that makes, I guess, Algebra 1 14 years ago. Okay, guys, so he's going to show you how easy this stuff can be. He's going to learn it for the first time, well, the second time in a long time. You ready? See this graph here? This is exponential growth. Do you see where it crosses the y-axis? The place where it crosses the y-axis is what we call the initial amount. So depending on what you have, whatever you initially have, if you have 50, 60, 1, 2, that is your first point. It's almost like your y-intercept, okay? The b is the base. The base should always be greater than 1. If the base is greater than 1, then it's a growth factor. I want to tell you, though, what b is made up of. b is made up of 1 plus the percent of growth. And that's going to be very important for you to understand. B is made up of 1 plus what?
The percent of growth.
Look how smart he is. Okay, and what is A?
Initial amount.
Very good. See how smart he is, everybody? A little bit about B. You got to make sure you understand B. Oh, this isn't on my other answer key, so hopefully I can do this. B is found by the increase or decrease from 1. Now I say decrease because eventually we're going to get to problems that are decay. There we I could spell decrease. Technically, B is 1 plus R. R stands for the amount, or percent would be a better word there. Percent of increase or decrease. It's either positive or negative. It's negative if it's decreasing, and it's positive if it's
increasing.
See how smart?
You are such a great teacher, Mrs. Langella.
Oh, thank you, Mr. Langella. You guys think we're really cheesy right now, but that's okay because it's making you, smile.
It's making me smile.
Oh, good. All right, problem 1. Modeling exponential growth. Economics. Look, this is your topic, huh?
Yeah.
Kind of. He could teach economics. He doesn't, but he's certified. Since 2005, so the amount of money spent at restaurants in the United States has increased about 7% each year. So, does that mean that people eat out more or less?
More.
That's because it's increasing. Now, in 2005, they're saying there was $360 billion that was spent at restaurants. That's a lot of money. Not too much of that is from my husband and myself because we're cheap and we eat in a lot. Okay, we're going to make the equation. Are you ready? We're going to do y equals. Now, what is the initial amount?
360
Now, this is in terms of
billion.
Okay, you guys see that? 360 billion. So what we're doing is we're actually writing an equation in terms of billions of dollars, okay? Now, that replaces the letter A. You remember our equation? Y equals A times B to the X. 360 is replacing the letter A because A stands for?
The initial amount.
Isn't that smart? A stands for the initial amount, okay? Now remember, there was a little hint on how to get B. Do you remember that? In this problem, B is 1 plus the percent that we have. So what percent did you read in this problem?
7%.
And 7% as a decimal is?
0.07.
That's right. And you guys, you never want to do 1 plus 7. You want to do 1 plus the decimal value of 7%, which is what?
0.07.
There you go. So therefore, if you add those things together, you get?
1.07.
And that is the value of?
B.
Very good. So we're going to do 360. Oh, that was my phone.
I almost ate a hair.
What?
There's a hair in my mouth.
We have cats. I don't know. Okay, so there's your equation. Can you imagine if we ever co-taught? All right, A and B. Now, there's your equation, guys. This is what we're going to use. If the trend continues, how much will be spent at restaurants in 2015? That's only a couple years away. Not even, my goodness, my phone's going crazy. All right, that's not even a couple of years away, actually. So let's go ahead and figure this out. We're going to do y equals 360 times 1.07, but take a pause, okay? Because 2005 is when this problem started. That would technically be year 0. So, Mr. Langella, if 2005 is technically 0, how many years have elapsed until 2015?
I'm going to guess 10.
That's correct because, you know, it's 10 years later. So you see this power? We're going to make it to the 10th power. And you guys have no clue what that is without a calculator, so we're going to use our calculator. Times, where are we at? 1 point to the 10th. Here's how much money is going to be spent in 2015 if the trend continues. Wow. We're pigs as Americans, aren't we? Cook at home, people. Cook at home. So we get approximately, or in Mr. Lankus language, he calls that squeakles, 708, not just $708, 708 what?
Billion.
Billion dollars. That's a lot of money spent at a restaurant. Now that's kind of crazy, isn't it? Starts at 360 and increases 7%. In 10 years, we've gone from 360 billion to 708 billion. Part B. What is the expression that represents the equivalent monthly increase of spending in 2005? Now what you got to do is you got to be real patient with me here as I try to explain this, okay? 1.07 was the number we got for yearly, I hope you agree with that. Would you agree with that? That's what we did above?
Yes, I would.
Okay. I hope you also agree then that 1.07 and that was to the x power, correct?
Yes.
Okay, that was to the x power. 1.07, tell me if you agree with this. If I give the numerator a 12 and the denominator a 12, did I really change anything right now?
No.
I really didn't, because 12x over 12 is still what?
1x.
1x, or just x. Very, very good. So smart. So right now we're trying to transition to show you how to write this in terms of months instead of terms of years. Okay, this is kind of a hard concept here, so try to pay attention. Now I know he doesn't know this, but you guys had better remember this. I could rewrite this as 1.07 to the 1/12 times 12x. Now, the reason I'm allowed to do that is because your rules from section 7.3 would tell you that if you multiply these together, you would get 12x over 12. Keep with me, okay? All I'm doing is I'm separating your exponent, and I know I'm not making a lot of sense now, but bear with me. I promise that I'm trying to help you. Now, you see the stuff inside? We're going to make that a new number. 1.07 to the 1/12 power is, we're going to carry this out all the way to that 6. We're going to make that 6 into a 7. 1.0057. And then that is to this power. That is to the 12x power. So what you need to understand is that this over here is in terms of years. So you can plug in years. This is in terms of months. But what we're going to do is, instead of writing 12x, we're going to put in a new variable, because x stood for years, okay? X stands for years. We're just going to use the letter M, and M stands for months, okay? So this is the B factor, okay? This is the B factor. If somebody asks you, well, what would this look like in 5 months? You would plug in 5 right here. So you have to change your year all the way down, and then once you get it to this number here, you have to put M instead of your 12x. M stands for months. Okay? If you don't believe me, let me try this. Asking my husband, because I want to try to show you that these actually are the same thing, okay? You said up here that it was 10 years, correct?
Correct.
Correct. How many months are in 10 years?
10 times 12, 120.
Okay, so I want to show you guys that if we plug 10 into this equation up here, and we plug in 120 into the equation down here, that we'll actually get the same thing, okay? So I'm trying to show you that they're the same. So we would do 360 just like we did before, 1.0057 this time to the 120, and we're hoping, again, we had to round, but we're hoping we're going to get close to the 708. Which we do. Again, the numbers are a little bit off because we had to
round.
But the idea here, guys, is that, yeah, this is absolutely the right way of doing it. Okay, so that was kind of long and lengthy. Let's get this one done. We can do this. Suppose that in 1985, that may have been when I was born. 1980.
Me too.
You too. Look at that. Suppose in 1985, there were 285 cell phone subscribers in a small town. The number of subscribers increased, no doubt, by 75% each year after 1985. That's a really, really big increase, okay? How many cell phone subscribers were in the small town in 1994? Write the expression to represent the equivalent monthly one. So we're going to have to do all this stuff up here. We have 2 parts to this problem down here, but we'll go faster this time through. Are you ready?
Yes.
Y equals, what was the initial amount of cell phone subscribers?
285.
Good. And we need to multiply that by the B factor. So this is A, okay? That was the initial amount. But remember, B is made up of 1 plus the percent. So what is the percent in this problem?
75%.
So we need to change that to?
0.75.
Very good. So B is actually?
1.75.
That is very good. Look how intelligent he is.
Everybody. Sharp mind.
Actually, why I married him. No, I'm just joking. All right. So our B is actually 1.75, and we're going to put this to the x power. Now remember, this is in terms of years. Okay, we'll do months on the other side. If our problem started in what year?
1985.
Okay, so 1985 would actually represent a 0 because it would be year 0. What year are they asking about?
1994.
So how many years from 1985 to 1994?
I was 9 years old.
That's right. We're going to plug in a 9, okay? So 285 times 1.75 to the 9. And that small town in that 9 years, if the trend would have continued, look how many, we're going to round to the nearest person, look how many cell phone subscribers there would have been.
It's not such a small town anymore.
Well, I wouldn't know what a small town actually is. That's not a small town?
No.
Oh, okay. Don't let him fool you. That's a small town. Because the problem says so. Alright, now what we need to do is we need to take this and we need to make it into months. Are you ready?
Mm-hmm.
So we're just really going to change the A or the B.
The B.
The B is correct. We're just going to change the B. The A would stay the same because the A is the what?
Initial amount.
Look how smart. Okay, so the initial amount doesn't change. So it would be, it started as 1.75, right? But that was in terms of what?
Years.
Years. So we're going to need to put an X up here. How could we rewrite that? How many months are in a year?
12 months in a year.
So we can do 12x over 12, and technically we haven't changed the problem because 12x over 12 is still what?
X.
So we haven't changed anything. The next thing we're going to do is we're going to rewrite it just like we did up here. So we're going to put 1.7 in parentheses to the 1/12 power and a 12x on the outside. And then we're going to put this into our calculator, and that's going to give us our monthly B factor. That's hard to say. Try saying that.
Monthly B factor.
Okay, so it was easier for you. Thank
Well,
you.
you said it first, so.
That is hard to say. You want to make sure you don't say any bad words whenever you talk real fast.
Exactly.
Okay, so we're going to use 1.0477. 1.0477. And that is to the 12x power. But this is actually still in terms of year. If I want to change this into a month, what do? I just change this into what letter?
M.
So 1.0477 to the m power. Now, if you don't believe that's right, I'm about to prove it. Are you ready? So we still keep our initial amount of how many people from over here?
285.
That is correct, neighbor. And we now are going to multiply that by the new B factor of 1.0477, but this time, how many months are in 9 years?
108.
108. That was fairly impressive.
I thought about it beforehand.
Oh, good. See, guys, we're coming up with pretty much the same answer again. Why are the answers a little different?
Rounding.
That's right. We had to round. But altogether, that would be the new B value. And I guess the entire equation would be 285 times 1.0477, but this time to the m power. Okay? So year equation, month equation. Flip. Compound interest uses this idea, okay? If you've ever heard of compound interest, how can I explain it? You know, I'm going to explain in the next video because this video is long enough.